the stream then. Open up a chat window. Okay. Sorry for the delay, everyone. We are back tonight with DanDoesData doing, one second actually, doing more Project Euler. I'm not sure how long I'm going to keep up this sequence. Part of why I do the videos is for my own education. Part of it is to do videos on topics that don't already have information. And Project Euler is pretty well covered, particularly the early problems, by a lot of different people since it's been around for a long time. But of course, like, as I was eating dinner tonight, I was thinking about the current Project Euler problem 3, so I was like, all right, well, I might as well keep at it. So, Project Euler, lots of math problems, math and programming problems that are nominally pretty solvable within a few minutes, in terms of you can do the computation within a few minutes on a standard computer. We're on problem 3. We did problem 1 and 2 last time to a certain degree. And this is the first one that's like doing a lot of primality testing, which this was my irritation with Project Euler in the past, that a lot of it boils down to how quickly can you test if a number is or is not prime. I mean, which is an interesting, important problem, but not one that I want to devote a lot of time to when I'm hoping to do more general kind of things. But the problem is, what is the largest prime factor of this big number? So this big number is this. The prime factor of a number is, prime factors I should say, are those numbers that when you multiply them together give you the resulting number. So if your number was, for example, 26, that's 13 times 2. Right, well, you can't assign that. Whatever. If your number was, say, I don't know, 128, well, that's 2 times 2 times 2 times 2 times 2 times 2 times 2. One more 2. 128. Also known as 2 to the 7. So you can have multiples of your prime factors. And the prime factors are the numbers that they have no number other than themselves and 1 as prime factors. So last time we solved this in like the stupidest possible way. And in fact, it did not finish, of course. It took way too long. And so that was an indication that we were doing something wrong. Just to work it with a much smaller, simpler example. Yes, and I'm going to need NumPy. Here we go. And so the way we did it is we walked up through each number up to the magic number n, and we said, hey, is this number a divisor? Does it evenly divide into it? And that gives you this list of divisors. And then you want to check which of these is prime and which one is the biggest prime. And the stupidest primality test you can do is to just literally take that number and test if every number below it up to some range. In this case, we're going up to all the way to half, which is more than you need to do. Check if every number below it goes into it. If none of them do, well, then it must be prime. And so you can do this. So this gives you the list of prime factors, and whichever one is biggest must be your magic number. So the slowest part of this equation is probably finding the divisors and then checking if they're prime. So obvious speedups here, where we're looking if a number is divisor, you don't need to go up all the way to n. You only need to go up to n divided by 2. If 2 doesn't divide n, well, then you only really need to go up to n over 3. So that saves you quite a factor already. And the primality testing. There's lots and lots of ways to check for prime numbers, depending on what the scale of the numbers you're trying to test is. What we're doing right here, that I call stupid primality check, is also known as trial division. You just try all the numbers below, see if they divide your number. And for like small numbers, that's actually a reasonable thing to do. When I say try all the numbers, you of course try all the odd numbers, and then you also try 2. 2 being the smallest prime and the only even prime. So you can save yourself a little bit of headache that way. So we did that here. Another thing, you don't have to go up to p over 2 if a number excuse me, you only have to check up to like square root p if those are any of those numbers are factors. Because if, for example, some number, if p over 2 is a factor of your number, then 2 is also a factor of your number, and you would have already found it. So you don't need to check all that silliness. But square root isn't always, in fact, if the square root is an integer, then it's definitely not prime. But if it's a float, you don't know. If it's a float, you don't know for sure. So if we say numpy dot square root, of course numpy dot taking a square root can be kind of expensive, so are you saving time? Is that right? Yeah, that's right. 529 is a square number? Never knew that. Maybe I did know that. Huh. What do you know? What we really want is there a floor function? Yeah, there we go. Say numpy dot floor of whatever the number is, of numpy dot square root of p. That should be right. But do you want to include that number? Whatever the number is, so we'll add 1. And we're going up by 2 here, but we're starting 3, so that's fine. So that is a vaguely faster. We've like saved some constants. We've cut off a little bit of work, but it's still gonna be horrendously slow. To the point where if you do this, you do this, cannot be interpreted as an integer. That's why I said floor, man. That doesn't. Ugh. Really? Really? I'd say numpy.int or something. Ugh. Silly. No reason for that not to. No reason for floor to give me a float. Okay. Sure. That's the same thing. And then you can run time it on this operation to figure out how long it really takes you. And you'll probably see that that's 37.5 microseconds. However, that's with the small number. We need to test a number that's actually much, much larger. So we need a better way to check if a number is prime, and also we want a better way to find the divisors of a number. Now, finding the divisors, that's factoring a number. There's, again, a lot of ways to do that. The stupidest one being what we're doing here, but the second stupidest one would be to take a range of numbers from n over 2 down to 2. Going down by -1. Look at that. That's incredible. List range, just to check that this works, 10, 0, -1. Does that do what I want? Yes. From 10 on down to 1. So start at the bigger number, because that's where we're going to find our winner first. Because we want the biggest guy. So let's make some new stuff. Better solution. So we're still going to do this in essence, but we're not going to iterate through everything. We're not even going to keep around our old information. We're just going to say, hey, are we a factor? Are we a divisor? Divisor. Which is to say, if n mod whatever number it is 0, then we're going to run some test. We're going to check, hey, are we prime? Right, is that what I want? Yeah, there's going to be an even faster way to do this, I imagine. Whatever the factor is. Alright, well, we'll just check is prime. I'll say if is prime I, print I break. So If we find the prime, say, hooray, we win, life continues. Otherwise, keep pressing on down. So we'll at least start in the most, so we don't have to save around our divs anymore. I don't need to import that again. So that, boom, gives you 29. Huzzah. Life is good, so you find it fast. However, this is prime function. There are many ways to do primality testing. One way you might think is like, well, why don't I just tabulate all the primes up to some large value, up to some number in which they might occur ahead of time. So I'm not doing whatever stupid thing I'm doing here every time. I'm just checking, hey, is this number in my magic list of primes? So there's ways to do that. You can like do the stupid solution, do is prime every time. An idea that's sort of like that is called the sieve of Eratosthenes. Let me see. Eratosthenes. Google will know what I mean. Eratosthenes, yes. Excuse me. Eratosthenes. Essentially what you do is you start at the bottom, start at the smallest number, you maintain a list of all the numbers through which you wish to check R prime. You start with the number that you have, you say, okay, mark off all the multiples of this number from my list. So you start with 2, you do that, and that gets rid of all the even numbers. You pick 3, that gets of all the numbers 0 mod 3. 4 is already marked off, so you don't have to worry about that. Then you do 5, you use 6, you use 7, and so all the numbers that remain are your prime numbers. And so here, each prime number is in a different color, which is actually a little bit confusing. Oh, they're over here too. So that's fine. So this is an old... This is an old algorithm that's been around for a long, long time. It's pretty quick, it's easy to understand. This gives you a list of primes. And the downside being you have to do it up to a certain value ahead of time is one downside. But we're gonna, for our purposes, we know the number we need to check up to this magic number. There's factors of this number that we need to check R prime. So I'm gonna say prime limit equals n divided by 2. That is the number up to which I wish to check is prime. And let's make a def sieve then. And sieve will take some number n, perform sieve of Eratosthenes. That might even be correct spelling. I think it is. Amazing. We accomplished nothing else. Excellent spelling will be on the list of things we wish to do. Okay. Oh my gosh, I'm already down a quarter at a time and I've accomplished nothing. Nothing. Sieve of Eratosthenes. So, you want to make a list of all the numbers that we have. So, primes, p primes for potential primes. And you'll need to say list range from 2 up to, we'll say n plus 1 to make sure we get n. And what you want to do, so you sort of want a for loop, but I think you want a while loop, really. We'll just say while true for the moment. No. We'll say I. No, I. Yeah, primes. I know. While p primes. While there's anything in p primes, we'll keep doing this. And primes will start off as an empty list. These are numbers that we have confirmed to be prime. While there's anything in p primes, well, p primes is true. We take the smallest value in p primes. So I say cur equals, is there a list? There's list.pop. There's no list dot like pop off the beginning. Or just pop. Remove and return item at index. Oh, that's exactly what I want. Equals p primes dot pop 0. So remove it, whatever's at index 0. Perfect. And then for p in p primes, I want to ask P mod cur equals 0. Does the current potential prime, oh, it's definitely a prime actually. That's true. So primes.append cur. If we get to this point, this number must be prime. If this number is divided by that, then we want to pop it out. And that's going to be list.remove, I believe. Remove first occurrence of value. Every value in here is unique, so that's fine. P primes.remove P. Oh, that's going to be new. That's going to burn me because I'm changing it in place. Let me just do that so I get like a copy of it. Actually, import copy? Is that a thing I have? Copy.deep copy? Yeah, there we go. Let me import copy. Import copy. Because I don't want to modify the list while I'm running through the list. That's a recipe for disaster. So we'll copy.deep copy just to make sure we're safe. Okay. I will remove that entry from my list of possible primes. And that's all. And then we return our primes. Whatever got added to the primes. Okay, let's see what happens here. And let's see what we screwed up. So if I put in 2, 2. If I put in up to 3, get 2 and 3. Oh, that's 4, excuse me. 3. 5, should include 5. 10, 2, 7, 9. Okay, good. I don't know, 100. 97, 89, all these things. I feel like just list of prime numbers would be a good thing to verify against, you know. Okay, 30. That's an easy. 19, 23, 29. Okay, that's all good. So this will sieve our numbers for us. And so we'll make a new is prime. We'll say is prime 2. I. Do I use N or I up here? I think I use I. P, of course. P for potential prime. And lazily check our list of primes. We'll say primes equals, so by default, let me make primes equal to sieve p limit. Yeah, let's see how long this takes. P limit is not defined. Oh, well, I didn't do that. What is that? N is a small number. So let's do that over here. That took, the fact that that took a measurable amount of time is concerning to me. Okay. 353 milliseconds. That's not going to be good. That's going to be really, really bad, in fact. I'm going to get burned so bad because when I raise N, oh man, I just know this is going to be terrible. Make new P limit. Oh boy, let's start running it. Yeah, oh, memory error. Yeah, that's not surprising. Oh. Yes, because the P limit is this number. So I would have to, let's see, I've got 300 billion things here, so I'd have to have 300 gigabytes. From the chat, never thought you'd see me doing Project Euler problems. No, I got my start doing Project Euler problems about 7 or 8 years ago. I recall being better at them then, or maybe I cheated and I switched to Sage. So there's an obvious problem here. If I start with this big honking list of primes, for whatever I want to do, I have to check all the numbers up to like 300 billion, and that's a lot of numbers. That's going to take like 3 gigabytes times 4? 300 billion? No, I have to use longs. Times 8. So, yeah, about 2.4 gigs. In theory, yeah, you can certainly store that, but that's going to be real expensive. Real expensive. So my devious plan to perform into civ Aristophanes, get all the primes up to some limit. Another question, shouldn't the prime be square root? If you're looking at one of the factors, a factor of whatever I'm looking at, of some number, that could obviously be up to n over 2. Because if a number is, say, I don't know, 100, well, 100, you could say, that's 2 times 50. I mean, that has other factors, obviously. But 50 is a valid factor of that, and you'd want to check, is that number a prime? Although the prime is only going to be up to n. No, the prime could be up to n over 2. Right. If our number is 26, is the number we want to find the largest prime factor for. The biggest prime factor will be 13, because it's 13 times 2. So you do need to check, get a list of primes up to n over 2, if you were solving the problem this way. However, the fact that this takes so much memory to get started, even though there's not going to be that many primes, you're going to have like log n primes. But maintaining a list. Although, hang on. It's just a pseudocode, not exceeding square root n. Oh, this is for if you want to determine if a number is prime. Right, and then you only need to check. Anyway, performance tips from Python Wiki. No spoilers. I will consider it. I want to blunder through this for a little while longer. I'm determining that the civ of Aristophanes is not really what I want to do, particularly not with a list. 2 point some odd gigabytes you could do with a NumPy array. Let's see, you can make an array, you can make an a range of 2 to n plus 1. Let's see, if I say 2, comma 10, is that inclusive? No, okay, yeah. D-type equals numpy.u int 64. So you can do this instead. And then wherever I have p primes, wherever that is, instead of removing, can you even do that from an array? You can't just remove. Oh, really? I don't have numpy array dot. It's terrible. Terrible. If I do that and I ask what are the things I can do, yeah, you can't just arbitrarily remove elements from an array. I don't want to spend an insane amount of time thinking about this. What you could do is mark it. And say p primes of, I don't know, I, whatever, equals false. False. There we go. Oh, then I just need bools. That'll save me trouble. Ooh. Bool. That is yeah, perfect. That might be able to stash in memory, no problem. So what's going to be faster is finding some factor, then dividing, and then finding a factor of that, and dividing, and we're whittling the number down so you're not checking every single dang number. So that might be a faster means of going about doing this. So get a bunch of prime factors, blitz through them, find some factor, keep working, do this, do that. I want to think about this a little bit more. You know what? Having a civ Aristophanes, that's a good thing just to have in general, regardless of Project Euler. Whether it's the correct approach in this problem having something like that is just a cool thing to do. So I'm just using the problem here just more as a prompt about how to think about this. Or a prompt is a prompt to work on something interesting. That's, to me, the real purpose of this. I find some bottleneck, whether or not this is the correct or fastest way to go about this problem, you might find yourself in a situation like this, where you get an out of memory error and you need to scale up your solution. Okay. So now I want to say, well, true in P primes I to the end. I to the end. Where I is like current I equals 0, apparently. Also, I can skip by 2. I'm pretty sure I can do that with A range. Can I? I love America. It's so good. It works. Fantastic. Okay. I don't want to start at 2, actually. No, that's not what I want to do at all. Oh my goodness. Start at 3. 3. Yes. However, if I have an array, how do I resize it? And where does the extra space go? Change shape and size of array in place. That will allow to determine references or views exist, resize, yada yada yada. Only contiguous arrays can be resized. Missing entries are filled with zeros. References are referenced by another array in this way. Really? Is like A range a special thing? Getting burned here, man. Getting burned. You know what? I'll just maintain. I'll just start the list at 2. That's fine. Yeah, that's totally fine. And if I don't want that, I'm not going to worry about the edge case where I put in a 1. So I've got all the odds. I can't pop anymore. I need to find a dot. There's like a find, search, something, something, something. There's no index, which is irritating. Search sorted. What is this? Find indices or elements V should be insorted in A in order to maintain. No. It's like I just want to find the first place that's true. Also, I don't want A range anymore. I just want zeros or something. Maybe I do want A range. Ugh. It's like I get the actual numbers, or I really just need to keep the truth value of it. I need to keep the truth value of each of these numbers. Right. So that is going to be of size n over 2. And minus 3 over 2, I think. And if I'm going about this entirely the wrong way, that's the nature of the beast, you know? That's the problem of doing these kind of things live when I haven't looked at the problem a whole lot ahead of time. I haven't thought about it off screen. And in fact, I haven't thought about this kind of operation in a long time either. Yeah, I feel like there's probably a better... Yeah, check a divisor, check if it's prime, or as soon as you find a divisor, divide. Find the biggest divisor. And it's not even find the biggest divisor. That won't necessarily guarantee you the operation. So as a total alternative solution, you could find first big divisor, work your way down, divide into your number. Now have two numbers, the divisor and the divisee. Not the divisee, the quotient. Such that find big divisor A, divide your number n. Now I have two numbers such that A times B equals n. And now you run the same operation, rerun on A and B. And you possibly fork out like a maniac. Alright, you know what? Let's actually think about this as a possibility. Is prime still in existence? Yeah, okay. Let's do it this way. Let's put the sieve down for a second, because I'm getting bogged down in some memory details. And so we should be saving ourselves some trouble all the time. So, by starting at the top, you can start at the top or you can start at the bottom. Doesn't really matter, I guess. And I'm going down to 2, starting at n over 2. I'm not including 2. Is that how that works? List, range. It's like it's always easier to just try these things than to have to look it up. Range 10 to -1. That does not include 2. Right, but if I had found 2 was a factor, I would have already found some other number, so I don't even need to worry about that. Maybe it would make sense to do this the other way, but I want the biggest number, so it's fine. So if we're a divisor, I'm going to need a dang function. Def find biggest. Find big div. Some n. Maybe I don't want to do this TQDM business anymore. That could get dangerous. If we're a divisor, then I want to say m equals n. No, I don't even want to do that yet. Then I want to run this on whatever I is. And I want to say m equals find n divided by I. Yeah. And then find big divisor of m. So we should be saving ourselves some trouble here. So I'm not checking if it's prime. I'm just dividing. And then we're going to find the biggest divisor of that number. This is right. I feel like I need to check if it's prime first. And if it's not prime, yeah, hang on. Else, and I just need to find the first divisor. So the moment we find something that's big, we don't need to find anything else. We're done. We're done with that. Else find big div. Of that. So I want this to be like A. This will be return I. I don't need to break anymore. And this will be like B equals this. So that'll be the other option, which is the biggest number from either one of these. And then we'll return I want the biggest number of either one of these. NumPy.max of A comma B. So in theory, this might work. So we're just going to go until we find a number that actually divides it. Let me try this with an n that's more reasonable and see if this actually works. Maybe this is what I did 8 years ago. I don't remember anymore. Let's see. If is prime and is prime totally works, right? 7 versus 9. And is prime is trial division right now. Just so we're clear. Find big div. Okay. And n. Whatever number n was. Float object. Okay, that's what I suspected. Really? That's not a float, pal. No, none of these are floats. Oh, but it's in some nested call. That's the problem. That's the problem. Right. And alright, let me turn the Python debugger. Do this. What's I? 29, which is a prime number. It's the first prime that divides this, perhaps, probably. Or wherever we are in this magic list. Right, so I divided by 2 is 14. Interesting. Okay. What is that? Magic things in the debugger getting burned. Print n. 7.0. Oh, that's no good. We go up. Print 10. Okay. Print m. Print m. Right. Because n divided by I ends the... God damn. Okay. Print n over I. Alright, so I know this divides it, so I can safely do integer divide. That was all. Now let's see. What the whoa. Okay, that's interesting. What do we got going on? Unorderable types, int versus none type. Curious. We go up a few ways. What's A? What's B? None. Okay. So it did not find anything. That's curious. So I hit some edge case where I go all the way through and I did not find any divisors. In which case I should just return the number itself as a divisor? No, then it would be prime. Oh, but this would... Is prime 2639. False. Alright. Import math. Math dot is prime? No, we don't have that. Okay. Nah. Is... It's like I want a primality tester to test my test. To test my prime list. You know what? Let's just... This is an easy thing. Boom. Is it a prime number? No. Divided by 713. Okay. That's fantastic. So why did it burn? Why did it burn and fail? Unorderable types. Yeah. So what is m in this case? M is 7. So when we operate on a prime number, that is the problem. So I don't check if m is prime, is the thing. Right? Else, if is prime m, return m. That's the alternative. The other number we found, if it happens to be prime, then we should just return that one. We might only get through one problem today, and that's alright. Find big div. 5. What is n? I don't think that's correct. I don't think that's right at all. I think that's very, very wrong. If it's prime, oh, you know what? A equals I. If it's prime, B equals M. Yeah, you don't need to stop and return right there. You return when you have both of them. Alright, let's see what happens. 29, which I believe was the answer I had before. The largest prime factor was 29. Okay. And the other magic question of time it. How long does that take? 458 microseconds per loop. Fun fact, how long did this take? Given the list of divisions, well, that's true. We were doing more before. Oh, no. Divs was... No, that's right. This was pretty fast, right. But making the division list, I'm sure, was not that fast. So let's just run it in here, and this is at least another way to solve it. Another way to go about thinking about the problem, even if this is also insufficient. But it all comes down to how fast a primality tester can you make? Which is probably going to be why I'm going to stop this stuff after a while. And you know what? I can print N, actually. I'd like to do that. Just to see, like, what factor am I on? And we're not going to find anything for a while. Yeah, okay, so we're just burning through our range here. Here's a good question. What if I say TQDM around this? What happens? How slow is this process? Yeah, you know, I'm doing a few million iterations a second here, but it's saying it's going to take 26 hours. If it wants to go through everything. But of course, we don't expect to have to find everything. And you could save time by just checking n over 2, checking n over 3. Again, like with list of primes, it's just like try... I guess, does it make sense to just start trying primes? Well, I don't have a list of primes. That is essentially the thing here. And you might be wondering, like, oh, what if the number is even? If you pass that in, well, then the first number is going to hit, because that'll divide it evenly, and then you don't have to worry about it. You'll hit right away. Start doing some stuff. Alright, so I'm convinced that this will work, but this is just all kinds of super slow. And it's like, how much do I want to keep thinking about this? Why does this even... I don't understand why this particular number has come up in this. I was expecting like Google to have an automatic thing. Oh, I know, I can make a URL and just call out to isprimenumber.com. That's funny. There are certainly faster ways to go about doing this. Ultimately, it comes down to how quickly can you factorize it, which is very closely related to testing if a number is prime. Or is it... Yeah, I feel like if I can look at just the greatest common denominator, is that a thing I get in here? No, that might help if I have a given number. But math dot... No, math doesn't even come with that. So the alternative being, forget that, crack open Sage. I don't have Sage? iSage? I thought I had Sage on here. Boo. Alright, well, oh bother on that then. So that would be the other alternative. Use a math-based program such as Sage. Python, Sage Math, which has all kinds of built-in stuff, has built-in primality testers, so you don't have to spend all your resources thinking, how am I going to test for primes in a fast way? I'm pretty sure Sage comes with an isPrime that's reasonably fast, and then you don't have to fret about that. And you can try to think of like, well, given a good primality tester, what is the best thing I can do here? So when you sort of like, what its idea is, how can I limit how many calls to isPrime that I'm making? So here I'm sort of only making a call to is prime at this point, and then I bust it down and sort of the subpoints, and you head on down. But that's the idea anyway. All right, we're ending a little early tonight. That's okay. I want to thank everybody for coming out. I don't know how much this Project Euler I'm going to do live on stream, and this is probably something for me to work out more on paper and just on my own. I might look at some things like, I think Hacker Rank is a thing. A friend of mine suggested like trying it out, see how you do, get some practice with things. So that's an option. There's also, of course, Kaggle competitions, which is like, that's more pure data science kind of stuff. So that might be something else that I look at. Do a similar type of problem, but on things that are more strictly machine learning or whatever. Math does have a GCD? I thought it did. Math.gc. Shows that I know. I did not find it. I bet it's right up here. Oh, yeah, it was right there. Didn't see it. Obvious failing. And fractions.gcd. Good call. So I might switch to doing some Kaggle stuff. That has the benefit that it is data science. You can sort of always get some kind of solution. And frankly, fewer people have probably looked at a lot of these. A lot of these are just like, go get started, figure out how to do stuff. No more competitions, that's it? Oh, these are active. No, show me all of the competitions. So, particularly the ones that have already passed and no one's going to care how you do. That could be an interesting thing to do. Or find one where there have been very few people have entered. That would be interesting. Sort by number of teams, but I want the fewest number of teams. Loading more competitions. There you go. Scroll down a little bit. Hold the scroll button. See if there's competitions where no one has entered. 0 teams. There we go. World Cup 2010. 7 years ago. 0 teams. $100. So maybe we'll do some stuff like that. Not actually enter anything, but just take a look at the data, see what's going on. All right. That is all we've got for tonight. So again, thank everyone for coming out. Oh, Amazon challenge. Interesting. I might check that out, Francois. Okay. Have a good night. Stay safe in the day, minds. Take it easy.